You hear it all the time, right? How much memory does your phone have? But have you ever really stopped to think about what computer memory actually is? I mean, it's not some kind of magical cloud floating inside your computer. Nope. It's a physical, brilliantly organized system, and today we're going to pull back the curtain and see exactly how it works.
I mean, seriously, think about it. Your computer right now is holding billions, maybe even trillions of tiny pieces of information. So how does it find that one specific byte it needs in like a split second? Well, the answer isn't magic, but it is an incredible system of organization. And it all starts with something surprisingly simple, a single switch.
Okay, so before we can build this giant digital library, we need to understand its alphabet. And believe it or not, a computer's alphabet is probably the simplest one you could ever imagine. It's literally made of just 2 characters.
And this is it, the humble bit. Every single thing your computer does. I'm talking rendering a complex video game, streaming a movie, even just playing your favorite song. It all ultimately boils down to a massive, massive sequence of these simple on or off switches, a 0 or a 1. That's it. That's the entire language.
Now, a single bit on its own, well, it can't say much, can it? But when you group 8 of them together, you get something really useful, a byte. And all of a sudden, with that simple little group of 8, you can represent 256 different combinations. And that's enough for every letter, every number, and all the basic symbols on your keyboard.
And here's the really key takeaway. This is crucial. While the bit is the absolute smallest piece of data, the byte is the smallest addressable piece. The computer doesn't really bother with individual bits. It thinks and works in these 8-bit chunks. So this is the true building block of our whole digital library.
All right, so we've got our building block, the byte. But a modern computer has billions of them, so how on earth do you keep track of all that? Well, let's use an analogy. Think of it like a library, a truly mind-bogglingly massive library. Just imagine a library with billions of books, but instead of shelves, they're all just dumped in one single gigantic pile in the middle of the floor. Total chaos, right? Trying to find one specific sentence would be completely impossible. And that's exactly what a computer's memory would be like without some kind of organizing system.
So, instead of that chaotic pile, a computer's memory is much more like this, a beautifully, incredibly organized grid of what we call cells. Just think of them as perfectly uniform little boxes on a massive set of shelves, and each box is designed to hold exactly one thing, one byte.
Okay, so if the memory is our set of shelves, and the bytes are the books, how does the computer know which shelf to go to? Well, it uses something that's basically the high-tech equivalent of a library's card catalog.
You know how it works, right? In a library, every book has a unique call number that tells you its exact location on a shelf. Well, it's the exact same idea in a computer. Every single one of those memory cells, every single byte has its own unique number, and we call it an address. It's such a simple idea, but with incredibly powerful results.
And this is the secret sauce to a computer's incredible speed, the central processing unit, the CPU, the brain of the computer. It doesn't have to go searching for data. It can just say, hey, give me what's at address 500, or store this piece of info at address 2 million. This system, it allows for direct, instantaneous access to any piece of information it needs. No searching, just grabbing.
So, we've got the system down. Bytes go in cells, and each cell gets its own unique address. Simple enough. But the truly mind-boggling part, the part that's hard to wrap your head around, is the sheer scale of this digital library.
I mean, we're all familiar with these terms, right? Kilobyte, megabyte, gigabyte. But when you see the actual numbers laid out, it's something else. A kilobyte, that's roughly 1,000 bytes. A megabyte, you're talking about 1 million. A gigabyte, that's over 1 billion. And a terabyte, well, that's just a whole other level entirely. Just look at that number for a second. That's over 1 trillion bytes. 1 trillion! That's 1 trillion individual addressable slots for data. So let's go back to our library analogy. Imagine a library with 1 trillion books, each with its own unique call number, and a librarian so fast they can find any single one of those books in the blink of an eye. That's exactly what your computer is doing, all the time, without even breaking a sweat.
So let's do a quick recap of this whole journey. We started with the absolute simplest foundation you can imagine, the on or off bit. Then we grouped them into bytes, which are kind of like the smallest words the computer can understand.
And then we gave every single one of those bytes a unique address, creating this perfectly organized system. And it's this simple, elegant structure that makes all the complexity and speed of modern computing possible.
And that really brings us to a final pretty interesting thought. This whole system, the byte and address system, it's a concept from the earliest days of computing, and it is scaled unbelievably well. I mean, it's just incredible. But as we generate more and more data than ever before, you have to start wondering, what comes next? What's the next great leap going to be? What will the library of the future actually look like?